Very good morning to all of you. Myself, Dr. Sivam Desai from Chemistry Department and Industrial Chemistry Department from the Parvati University. First of all, I would like to thank Dr. Devmale Bunya. So for precious time he spent and within short period, he accept our that request to get webinar. So, sir, welcome you on the international webinar on chemical biology and its potential application for the future scopes. So, welcome, sir. And I'm also welcome to audience to join the webinar. So before the start the webinar, I have to just brief introduction of Dr. Devmale Bunya. So right now, Dr. Devmale Bunya is a scientist position at the Cloud Spring Herbal Laboratory at New York, USA. And he have also very vast experience after the PhD. He also have one postdoctoral experience through the Ohio University, State University, Columbia, USA. And sir also complete the PhD from CSR, Indian Institute of Chemical Biology from Bangalore, Bangalore. And sir also complete his MSc with gold medal from Central University of Madhya Pradesh. And sir have also that earned that 3 international US patents. And during the research time, he published more than 25 renowned or high impact factor journal like JAX is there, ChemCom is there. So people are dream to publish in these types of journal. So sir, I have very good research paper publication more than 25, and sir have also have experience to present oral presentation and poster presentations in the various webinars and conference. So we have running short of time, so I can request the Dr. Devmale Bunya, so we can start the session of today's, that is chemical biology, potential application and future software. Shall we start, sir?
Yeah, sure.
Over to you, sir. Fine. Thank you.
Thanks, Ivan, for these introductions. Good morning, guys. Hope you are all doing great. My title of the webinar presentations is that the chemical biology and its potential applications and future scopes. So before doing the presentations, I think I should give my brief introductions. I did my BSc in Chemistry Honors from Vidyasagar University in 2009, and then I did Masters from the Guru Ghasidas Central University in 2011, and then I also worked in the Huntsman Corporations, that is in Baroda, for 1 year, and followed by I did research at Central University of Gujarat, where basically I met with Sivang, and then I did my PhD from the Indian Institute of Chemical Biology from 2013 to 2018. And then I moved to the Ohio State University, which is in Columbus, Ohio. And I worked there for 2.5 years. And from the last year, in 2021, I'm working at the Cold Spring Herbal Laboratory. So my topic, I have decided to split into 3 portions. One is that the chemical biology. In these portions, I will describe the brief introductions and what is the difference between the chemical biology and the biochemistry. And second portions, I will describe the research summary. This is basically, I will show my brief research work, which I did in PhD and my post-PhD. And the third portions, I will maybe explain the future scopes, what is the potential directions for the job finding or the research. So in the introduction side, we should know what is the chemical biology. When the term chemical biology comes in mind, so everyone thinks it is the chemistry and biology. Yeah, it's right. the definitions of the chemical biology is that the applications of chemistry to solve the biological problems, or we can say to assist the biological research by using the chemical tools. In little elaborate, we can say maybe the designing and the synthesis of small molecules, peptides, peptide nucleic acids, and their potential applications for the biological complications. We can say particularly in disease, different types of disease, etc. Um, so in a paper which is published in 2005 in Nature Chemical Biology, that paper, they have explained very nicely what is the chemical biology. Basically, this is the new integrations or the sum of all the sub-disciplines of the biological chemistry, which is merged with that the biochemistry, bioorganic, biophysical, bioinorganic, and bioanalytical. So all these sub-disciplines are in integrations we can call the chemical biology. Now, there is some misconception that the chemical biology is the biochemistry. Yeah, both are not exactly same. They have some differences of these two terms or the two subjects. The chemical biology, as I mentioned before, this is the applications of the chemical techniques to study and to manipulate the biological systems, whereas the biochemistry is the study of chemistry, which is happening in the biological phenomenon. I can show some topics or the research topics which is related to the chemical biology that will make more understandable. In the first, we can say the designing and the synthesis of unnatural nucleic acids, peptide nucleic acids, and peptides to treatment human diseases. And second is that to the design unnatural amino acids or sugar synthesis for ion channel modulations and glycosylations. And the third one is that the DNA preservations and cellular organelle leveling. In the DNA preservations, now I'm working on that. Basically, it is to preserve the genetic DNA on the solid surfaces so that we can store that one for a long time. And whenever we need that, the DNAs, we can go for the amplifications and we can do the further research in any time. And the fourth is that the development of the biocatalyst so that we can use the modern or the developed biocatalyst for the molecular biology. The fifth is that the efficient drug delivery. We can use the liposomal model or the peptide vesicles that can be used for the drug delivery in vitro and in vivo systems. Another is that the efficient bioconjugations. So this is important for the leveling of for the leveling with the dye to detect the organelle inside the cells. Yeah, inside the cells. So we can use these techniques, the click chemistry or other well-known chemical techniques. Whereas in the biochemistry, the potential topics are that the study of the metabolisms of the amino acids and the study of the carbohydrate, lipid, nucleic acids, etc. And the second is the understanding how the proteins translated to discovery of the new pathways development. Yeah, and the third is that the cycling D, which is required for the phosphorylations and the DNA synthesis, because the CDK4 and CDK5 plays important role in the cell regulations. So on this topic, the research is also going on. The fourth is that the cytokinase and the hypoxia. So hypoxia is the conditions in the biological systems where due to the cells are stressed due to lack of the oxygens. The peoples are also working on this in this research area. So we can say that in the chemical biology, we need to do the new synthesis or some synthesis based on the organic chemistry tools or the chemical tools, and that can be applied in the biological field. Where in the biochemistry you no need to do for the synthesis, or you can study further to reveal the new pathways which is related to the biology. In the second portions in the research outcomes, I will show some of my research work, and it's due to time constraint, I will not show all these things, but I will show in brief what the work I did in my PhD and in my post-PhD. In the first portions, the applications of the peptides and the peptide nucleic acids. So what is the peptide? We know that the peptide is that the amino acids, when the amino acids are conjugated through the amide bond, is called the peptide. When the two amino acids are connected, dipeptide. When three is that the tripeptide, and we can go for further. There is a very good applications of the peptides. It is applied for the drug delivery purposes, anti-cancer, antibacterial, antioxidant, tissue engineering, and the cosmetics. The well-known anti-cancer drug is that the PNC27, that is probably the 24 peptide sequences. The beauty of this peptide is that it can only target the cancer cells, but not in the normal cells. After the peptides, the people are interested on the work on the peptide nucleic acids. As you see that this is the structure of the DNA. We know that DNA is combined with the nucleobases, that is the ATGC for the DNA, and for the RNA it is AUGC, and there is also the sugar and also the phosphate. And so in the peptide nucleic acids, what happened here, the sugar and the phosphate linkages are replaced by the pseudopeptide skeleton. So that's why it is called the peptide nucleic acid. So now the question is why the people are interested on the peptide nucleic acids. The reason is that the PNA, it has the structural similarity with the DNA and RNA. It can also interact with the DNA and RNA in a sequence specific manner, and it can also stable towards the enzymatic degradations. And the most importantly, it can also recognize the double-stranded DNA and the double-stranded RNA. So these are the importance of the peptide nucleic acids. In one applications, this work is done by the Lorex, and they have published in 2014. They have combined the peptide and the PNA, peptide nucleic acids, and that has been treated for the mRNA. So they have used the cell-penetrating peptide, that is the octarginine, and then they have designed one mRNA targeting PNA, and then they treated inside the cell, and that can silence, or that can register the mRNA activity. So in this way, they have worked to silence the mRNA sequences, so that if mRNA is inhibited, then through the mRNA to protein synthesis can be stopped. That is called as a translation. The powerful tool is to combine the peptide and the PNA is that the click chemistry. So here the Ruthman in his paper, The Cancer Gene Therapy in 2017, they have used the proline with the modified, which is the alkyne modified, and the PNA, which is modified with that the azide one. So both they have synthesized under the solid phase SPPS, solid phase peptide synthesis, and then they have combined by the QAC technique, that is the copper assisted azide alkyne cycloaddition reactions. And after the synthesizing this one, they have did the purifications by HPLC and then MALDI. But nowadays, the people are not using the QX reactions because the copper is cytotoxic, so it can damage the DNA and RNA. So the people are interested towards the copper-free reactions, which is one is known as that SPAC. That is the strain promoted azide alkyne cycloadditions. So as you see here, this is the the cyclooctane. Here, this is the SP hybridized, but it is strained. So to release this strain, it interact with that azide one under the physiological conditions. So there is no need of any copper or any catalyst, and it can transfer to its product. So, but the reaction rate is little slow, but is good that it is not being affected by any copper or anything else. And another, the third generation click chemistry. Here, the people are used that the TCO, that is the trans-cyclooctane, they have used with that they have used the tetragen. So here, the two macromolecules are combined here, and that are being transferred very fast. So as you see here, the reaction rate is very fast. It is up to the 10 to the power 6 ranges, which is much faster than the QAC reactions and SPEC reactions. So the people are trying to develop this one. This is not that much old. This is very new. People are working on that. And in the applications too, is that the development of the non-canonical nucleobases. So we all know that there are the 4 native nucleobases, or the 4 native canonical nucleobases are known. That is the AT, GC, and U. So this is the GC, which are the has the 3 hydrogen bonded, and the AU, the 2 hydrogen bonded, and AT is also similarly the 2 hydrogen bonded. So the scientists are now thinking whether we can go beyond these 5 nucleotides. So they are working on that, and we have developed one non-canonical or the non-native nucleobases that is known as the melanin. This is the M that signifies the melanin. The beauty of this one is that it can interact with the threonine in the both side, which is interact on the both sides. So this is called the bifacial. So it is so similarly it can also interact with both U, and also that is in RNA. It is also in DNA, and it is bifacial because it interacts on the both side. So if we combine this one, the bPNA, due to the bifacial PNA, which is consist of with that the melamine, this one melamine and this one melamine, and here is that any canonical nucleobases, and this is the DNA, so that it can orient itself, so that it can interact with between two faces. And this is much stronger, the PNA DNA interactions, because it interacts on the both sided. Yeah. For doing this, we did a lot of synthesis. With that, first we prepared the native aldehyde, native basis aldehydes, and also non-native aldehyde. Then we have attached bicovalently on the side chain of the lysine, and we form the K axis. K is the lysine, and the 2 axis may be the native or non-native nucleobases. And after that, we formed the bifacial PNAs, and we have shown the applications in that the MALA1 gene, so which is responsible for the lung adenocarcinoma cells, which is responsible for the lung cancer. Yeah, this is this gene is overexpressed in the lung cells when the people are affected with the cancer. And these are published in the last year. As I mentioned before, that the PNA and DNA interact is much stronger than the DNA duplexes. So we did this experiment. So we took the DNA. This is for 8-mark DNA, and this is the PNA is also the 8 sequences. I put X and Y because this is not published, so we are working on that. We have checked the thermal denaturation assay, where we interacted with the DNA with the PNA1, and on the other side we did the both DNA duplexes. After the formations of the complexes, we did the melting assay, and from this melting assay we checked that the to break these complexes we need the higher temperature compared to that the DNA duplexes. So we can say the PNA DNA duplexes is much more stronger than the DNA duplexes. In the applications 3 or in the work 3, so I worked here in that the peptide as an antimitotic drug. So the antimitotic is that the drugs or the molecules which stop the mitosis cell division. We all know that the human body is made up of the bones. So similarly in the cells, the cells are made up of microtubule. So these are the microtubules. Microtubule is a key cytoskeleton protein which makes the cells which makes the cell space or the cellular structure. Yeah, and also the cellular functions. So the microtubule plays an important role in that the cell divisions, because we know that in cancer, what happened, the cell division rate is rapidly enhances. So we are thinking to target the microtubule. If the microtubule are disrupted, then the cell division's growth rate will be inhibited and the cancers can be prevented. We know that there is the cell divisions, the pathways are the prophage, metaphage, anaphage, and telophage. In the prophage, what happened, the nuclear envelope has been disappeared and the chromatins are aggregated, and in that metaphage, the chromatins are aligned, and in anaphage, the microtubules are connected with the kinetochore, and it pulls the chromatins on the two opposite directions. And in telophage, both reaches the other two directions, and the two sister cells are formed. So we designed the peptides which targets or which destabilizes the microtubules. Now why we did the peptides? Although there are some mitotic drugs in the market, the well-known antimitotic drugs are the paclitaxel or taxol-based drugs, and also the colchicines. But the problem is that it has the several side effects. These are the poor water soluble, it has the low bioavailability, and also the less specificity. So that's why we choose to work on the peptide, because the peptides have the excellent bioavailability, and it can also bind the tubulin. It has the low toxicity and high uptake efficiency. All these factors lead us to work on this peptide, which will act as a antimitotic drug. So we know that the microtubules are formed with the tubulins. So the tubulins basically made up of the two subunits. One is the alpha tubulin and another is the beta tubulin. So alpha and beta combine and form the tubulin. And when the multiple tubulins are formed, then it forms the microtubule. So and the GTP in cells, that is the polymerizing effect. So it helps to form tubulin. It helps to form microtubule from tubulin. So there is a specific site where the GTP binds at the beta tubulin and enhances the microtubule formations. So we target that GTP site if our designed peptide will bind at the exchangeable GTP binding site where the GTP binds, then the GTP will not bind at particularly that site, and then the microtubule formations will be disrupted. Based on this hypothesis, we have designed some peptides based on that in the docking study, and we also measure the binding energies of that one. And as the docking is the theoretical study, we need to go for further to study for the cell-based study. So that's why we took all these designed 5 octapeptides and did the cell viability assay and observed that the PP2, that the peptide 2, that sequence is PRA-SHANT. All these all these are the natural amino acids. And interestingly, we observed that the IC50 value is 37.8 micromolar. Although it is not that much cytotoxic, because 38 is not efficiently cytotoxic, but we can say it is moderate cytotoxic. And also it is much higher than the previously reported Plagix peptide, that is the 12-mer sequences, whose IC50 value is much higher, it is 180 micromolar. After that, we also did in other different cancer cell lines, that is B16F10, MDM231, HeLa, and A549. And in all these cell lines, our designed octapeptide is so its potency. And then we tagged by the chemically on the N terminals with that the 5,6 carboxyfluorescence to identify whether our peptide can enter inside the cell or not. So that's why we marked the nucleus. We track the nucleus by the host dye, and after 2 hours incubations with the fluorescence tag the peptide, we observed that the peptide goes inside the cell. And this is the merged images, and it shows that peptide goes inside the cell. And this is the 3D images of the cells. Yeah, it is inside the cell. And also we checked that in which pathway it goes inside the cell. We checked that it goes in the temperature dependent manner. We incubated 2 sets of cells, one at the 4 degree and one at the 37 degree. We checked by the flow cytometry that the uptake is higher when the cells are incubated at 37 degree. And this is one study we did, the control peptide, which is without arginine. And we saw that in our sequence, that is which are PRASANT, which have the monoarginine, which also facilitates the higher uptake. Then we also check the morphology. One is untreated and one is treated. And after 24 hours treatment, we check that the cell morphology has been disrupted. And another study we also did, that is we strained microtubule with that the primary and the secondary antibodies, and observed that in control without untreated peptide, the cells are happy and looks healthy. But in treated octapeptide, the cells becomes bundle-like and it is synced. So yeah, there is definitely the potential effect of the octapeptide. And we did some chemical synthesis on the glass slide to check that whether the microtubule can glide on the glass slide. So that's why we make the 2 cm functional glass slide. We did the chemical reactions on the glass slide. We did the dual functionalist, one is the 2-century and the biotin functionalist. Some afterwards study, I will also show these glasses. So the 2-century is needed. It can interact with the proteins. So that's why we labeled, or we make functionalizations with the 2-century and also the biotin. So this is the schematic diagram, how the glass slides will interact. So basically, this is the 2-century containing glass slide, and we did the UV light at a particular portions. There is some positive mask. So through this way, the UV light cannot be passed through. But in this way, in this side, the UV light can go through. So that's why it will be destroyed. And then we have washed everything. We add the nickel, and then we add our protein of choice with the histone tag. So the nickel will bind with the histone. So that's why we prepared these glass slides. And the real applications is here. What we did, the glass slide, which has the 2-century and biotin-related functionalizations that I mentioned before, and then we add the kinesin histone protein, and then we did the GMP CPP stabilized microtubule, and in that we also did the biotin-related octapeptide, which I shown has a interesting effect on the microtubule, that is biotin tagged, and that biotin is attached on the N-terminal by the solid phase peptide synthesis, and we observed that in control there is no peptide, no interacting peptide, so the microtubules are glide on the slide very fast. But in the second case, where there is a peptide, the microtubules are interacting with the peptide, so its gliding speed is very slow. So we can say here the microtubules are happy and moves very fast, but in that second case, it can't move too fast. And we also measure the speeding gliding speed limit, gliding speed calculations, and we see here that the gliding speed is very high compared to the treated peptide. And the last one is that we also did, we're also interested whether in that the 3D cellular model, our peptide goes inside the cell or not. So that's why we prepared the tumor mimicking spheroid made up of the MCF7 cells, and we treated with the host dye that's in the nucleus, and also we treat the peptide for the 2 hours incubations, and we checked in confocal microscopy, and we saw that it is it has the good uptake. It is merged images, so we can say that our octapeptide can go inside the cells. And we also, and after that we also checked that whether our generated the tumor spheroid can inhibit its volume. So here we, after tumors spheroid formations in MCF7 cells, we have the similar sizes of the 3D spheroid, and then we go for treatment. The upper portions there is untreated, the no peptides was treated, but in the second cases, the octapeptide PRSNT, the percent peptide that has been treated, and we saw that there is a significant growth inhibitions. But in that the untreated, there is a significant amount of the volume, that tumor spheroid volumes is increased. There are other lots of studies we did in this paper, but I saw in this one. So we can, in conclusions, we can say that our designed octapeptide strongly binds with the tubulin at the exchangeable GTP binding site. Second one is that it significantly inhibits the tubulin polymerizations and also reduces the kinesin-driven microtubule gliding speed. And third is that it also inhibits the tumor spheroid growth. In the fourth applications, we have we have chosen one peptide sequence is long peptide sequence, and that is published in the Nature Biotechnology. And there they have shown that their chariot peptides go inside the cell. And interestingly, they have um, uh, the di tryptophan units. So we are trying to explore whether this what's the main role of these tryptophan units. So is that equally efficient when they are the the close, or whether they are the far away? So that's why we designed the 12 the tetrapeptide, and we checked first the cell viability, and we observed that the all are the non-cytotoxic. And then we tag all these 12 peptides with that the fluorescence molecule, and then by FACS we check the cellular uptake. And we saw interestingly that when the tryptophan units are very close, they have the good uptake efficiency. And we also worked on the glass slides, where I mentioned before that we prepared the biotin glass, we did the streptopidine, and also we did the double-stranded DNA. So the DNA is labeled with biotin, and also the TRITC red dye. We all know that we know that the biotin, streptopidine biotin, has a strong interaction, so that the DNA are attached here. And then we washed everything, and after that we treat the fluorescence tag the tetrapeptide. And interestingly, we observed that when the tryptophan units are very close, these are binds with the DNA. So if you see that all the six have a strong binding with the DNA, but when the two tryptophan are far away, not close, that are not binding so efficiently. And then this is the masked images, which indicates the efficiency of the tryptophan units. After that, we did lipopeptide. With that, the tetrapeptide, we attached the long chain to make the peptides is hydrophobic. So we took the bromohexadecan, and we attached on the monobox protected ethylene amine, and we form the NN dihexa ethylene diamine. And then we attached on the N terminal of this tetrapeptide. Before that, we attached the succinic anhydride to make this side acidic, so that the acid amine coupling is possible. And after that, we cut the resin. And this way we synthesize the lipopeptide. After that, we prepared the liposomal lipopeptide. Then why we interested to add also the liposomes? Because the liposomes can efficiently load drugs inside it, so that it can specifically release the loaded drug at its specific positions. So to enhance that the tumor microenvironment drug release, we use the liposomes. So we loaded with that E3 our designed lipopeptide, and then the liposome, and also the doxorubicin. We used here the doxorubicin drug, and we prepared the liposomal long chain attached peptide, which is encapsulated with the doxorubicins. And after that, we checked that in the 3D tumor model, and we also measured the size of this CPD by the DLS, and then we checked the IC50 value in MCF7, and it has very significant effect of the 2.7 micromolar. But we are interested this time for the mice model, so that's why we change from MCF7 to B16F10, because B16F10 is that the mice melanoma cancer cell line. So here we also check that it has the significant potency. After that, we took the two different types of the mice. We took that the C57BL black mice, and we divided into two groups. One is untreated and another is the treated. and untreated both the mice, we injected with that the cancer cells, and after 1 week there is a tumor generation happens, and in the treated cells we give our liposomal lipopeptide we treated at day 1 and day 8, and interestingly we observed that the tumor volume in the treated cells is decreasing, where in untreated cells, in untreated mice, the tumor volume is increases. We measure each day up to the 2 weeks the tumor volume, and also we measure the body weight, and we saw here the body weight is also increases for the treated mice, but the untreated, the tumor are growing fast and the body weight is also decreases. So in a conclusions, we can say that this tryptophan containing the peptides can interact with DNA strongly, and it can also strongly inhibits the tumor growth in mice model. And another work we did that we choose the one another tetrapeptide, that is HWGF. This is already reported cyclic and decapeptide that is that has an effect on the effect on the tumor growth on mice. So we are thinking that this HWGF small peptide, which is consisted with the hydrophilic unit and hydrophobic unit, so it can possible the peptide vesicles, and in the peptide vesicles we can load the drugs, and which can be treated in that in the cells. So that's why we incubate for the 4 days, and we saw that this HWGF short tetrapeptide forms the peptide vesicles, and then we also load the drug. We use the doxorubicin drug. This is the TAME images. It is the left side is that the only HWGF peptide, and the right side is that the drug loaded peptide. And this is the AFM images where it shows that the hollow vesicles of the peptides. This is the height versus height versus distance graph, and this is the peptide vesicles, but this is the drug loaded peptide vesicles, and height versus distance. We saw that it shows the drug loaded peptides. So drug loaded drug loaded peptide vesicles, and this is the peptide we synthesized and the purified by HPLC and did the mass by Maldi. And we also did some other assays. One is that the cell migration assay. Here we treated that only doxorubicins, and another is that the doxorubicin HW peptide, because HW can target the MMP, matrix metalloproteinase. So that's why we treated in all the 3D cells, and after 24 hours treatment, the first one is untreated. We saw that the cells are migrated in only doxorubicins, that cells are migrated, but the rate is lower. But in HWGF loaded with doxorubicin, the cell migration rate is slow. So we can say that this MMP9 targeted HWGF peptide vesicles can significantly deliver doxorubicins inside the MCF7 cells. Yeah, and this is my the research finding, and in the future scopes, I can say that there is lots of work is going on the chemical biology. There is you can go for the industry, you can go for the in that academics, and you can go for the academic research, and there are also other studies or other jobs can be done. In the industry, we know that in the industry we people did the target identifications, and from the small molecules or the peptides or other target molecules they are prepared in the library, and they also designed the lead candidates, and also they did the mechanical studies and did the clinical trial. And for this one, we people needed for the R&D's sector, and also needed the chemical biologist. And some companies like the big pharma companies, Pfizer, Moderna, they also recruit the postdocs for their studies. So there is a huge scope for this subject. And in the academic sector, there we can have the teaching jobs and the faculty jobs in India and also in abroad. And yeah, and also in that we can continue the research after PhD. We can do the postdoc. We can do the research assistant professor, research investigator, senior research investigator. These are depending on the experiences you will gain. Yeah, and with that, there is a lot of scopes in India and also in abroad. In India, and there is a CSIR labs, DST, DBT, the labs are available, and they are also doing the great researches. And in abroad, yeah, there are they also recruit the students and the researchers. And yeah, beyond that, there is some other industries job scope. That is that the patent officers, the various universities and research institute, they hire the patent officers for the patent writing, submissions, and communications purposes. And there are some the journals, chemical biology journals. They also recruit the positions for the assistant editor and the chief editor, publishing directors, all these things. And yeah, and also the clinical chemist in the medical labs, they also recruit the chemical biologist for the studies, the DNAs and cells of the patient, the samples taken from the patients. Yeah, there is a lots of scopes, I can say. Yeah. Thank you. And I end my presentations.
Okay. Thank you so much, Dev.
I think I take a long time. Yeah.
No, that's fine. That's fine. So, audience, if you want to have doubt, so you can drop in the live chat, so we can take that question or doubts during the sessions. So, meanwhile, I have to say the thanks to Dr. Dev Madan. So, because right now in the US, maybe near about
yeah, it's 9 to 1:30 almost.
okay, fine. So thank you so much for that. Spend your precious time to us. And sir have elaborately present the basic from the peptides to the research level. And sir also describe the how you characterize, how you can study the pharmacokinetics, pharmacodynamics, and basic characterizations of the peptides are also discussed. So thanks a lot, Dev sir.
No problem. Yeah, you can call me by
Yes,
Nirmal.
fine.
No need
Fine,
to call.
fine, fine,
Sorry,
fine, fine.
I feel embarrassed.
So, yeah, okay, fine. So, and I have also would like to thanks from the Department of the Chemistry of Param University and Industrial Chemistry Department. And I would also like to thanks the audience, though who patiently spent 1 hour for the international webinar. And let me check whether that any comment is there or not. Just give me 1 minute for that. Then we will take that down. I think in the chat there is no any doubts for the audience. So I would like to thanks from the Parul University as a gift of tokens, the Parul University that gives the certificate for the Dev.
Yeah, I'm also thankful to the university, Pal University, and the organizers, and also especially to you for communicating with me.
Yes,
And it's my great pleasure to present here.
okay, fine. Thank you. And last but not the least, that IT coordinators who,
Yeah, yeah.
without any troubles, that we can successfully arrange the webinar. So, and the branding committee also, I would like to thank. Okay. So, I hope so. We can great success in the life. And in the last notes, be positive in the life. We can do the success in the life. Okay. Fine. Thank you, sir. Bye.
Thank you. Bye bye.
Bye.